Welcome to this video lecture on Castigliano's theorem to find deflection in a beam, which we study in mechanics of materials or in strength of material. Now when we find deflection in a beam, there are various methods to find out the deflection. Now when we study the strain energy methods, under this we have to study this particular theorem, which is called as Castigliano's theorem. Now before discussing the statement of this theorem, let us first discuss about this scientist whose name is Alberto Castigliano. Now this Castigliano's theorem, which is one of the most famous theorem in structural analysis, which was discovered by Carlo Alberto Pio Castigliano, who is an Italian engineer. Now Alberto Castigliano in 1873 described methods to find deflections and slopes in a beam and trusses, as it was the part of his dissertation for engineering diploma. Now which is famously nowadays it is called as Castigliano's theorem. Now basically when we are using this Castigliano's theorem to find out the deflection, particularly it is called as Castigliano's second theorem. Now which provides for finding the deflections of a structure from the strain energy of a structure. Now to understand the concept of this Castigliano's theorem, let us see one example of this simply supported beam. Now here in this diagram you can see this is a simply supported beam which is subjected to a number of applied forces. Now here it is P1, P2, Pi and Pn, means n number of forces are acting on this simply supported beam. Now under the application of these different point loads acting on this beam deflect like this, and at the same time at different points, means when these point loads are acting on the structure, the deflection takes place. Let us say delta 1, delta 2, delta 3 and so on. These are the displacements under the point loads P1, P2, P3 and so on. So now if we are interested to find out the displacement, that is delta 1 or delta 2 or delta I or delta n. So in general, if we are interested to find out the displacement under any point load, how we can find this part we have to discuss in particularly Castigliano's theorem. Now let us see first the statement of this Castigliano's theorem. The statement is that if a total strain energy of a structure is expressed as a function of set of applied forces, then the first partial derivative of strain energy with respect to the applied force gives the corresponding displacement to that applied force. Means if we have this equation of U, that is called as total strain energy of a structure when it is subjected to some different forces. In this case now, if this total strain energy is expressed as function of applied forces like P1, P2 and P and so on, in this case when we take the partial derivative of the strain energy with respect to the applied force gives the displacement at that particular applied force. Means if we are interested in this diagram now, for example, if we are interested to find this displacement delta 1, in this case we have to take the partial derivative of the strain energy with respect to P1. Similarly, if we are interested to find out this delta n, that is the displacement under a point load Pn, in this case we can take the partial derivative of strain energy, that is U, with respect to Pn. You will be getting the respective displacement as a delta n. So in general we can say it is dA by U by dA by P is equal to delta, that is first partial derivative of strain energy with respect to the applied force gives the displacement under that particular point load. Okay. Now when we are discussing about the deflection or displacement in a beam, when we are using this term, that is dA by U by dA by P is equal to delta, now here we have to first find what is this U, which is called as a strain energy. Now when we consider the beam, which is a simply supported beam, generally we say it is a flexural member. So we should know that the strain energy for any flexural member is equal to integration from 0 to L, it is m square upon 2 EI into dx, where this m or mx is the equation of a bending moment for that particular part of a beam. So in general, this total strain energy for a beam which is a flexural member is equal to integration mx square upon 2ei into dx. Means this integration is with respect to dx. Hence, now when we put the value of this u, that is value of u, that is total strain energy, in this above equation of Castigliano's theorem, then we get the displacement delta is equal to dabba by dabba p of this term, that is u. Now when we'll solve this integration, finally, as if ei, that is flexural rigidity for that particular member, is constant for the whole length of the beam, then you can take it outside. So finally you will be getting equation of delta is equal to 1 upon ei integration from 0 to L mx dabba mx by dabba p with respect to dx. So by using this equation of a displacement, we can find the deflection in a beam anywhere along the length of the beam where the point load is acting. So to understand this concept, let us see one example. Now the example is that a simply supported beam of span L subjected to a point load, which is shown in figure. Find the deflection under a point load using Castigliano's theorem. Now here in this case, this is a simply supported beam which is subjected to a point load P at a distance A, which is at a point C. Now the total length of this beam is L. So at A and B, as it is a simply supported beam, reaction will be there, that is RA, and reaction RB will be there. Now before solving this example, we can easily find out the reaction at A and reaction at B by using conditions of equilibrium. So the first equation we can use, that summation of moment of all forces about point A is equal to 0. So when we use this equation, we can take moment of this RB and moment of this P about A, and we can easily find out the reaction RB, this is equal to PA upon L. Now when we'll take summation f of y is equal to 0, we can find easily RA is equal to, that is PB upon L in this case. So once we get RB and RA, then we can think about the Castigliano's theorem to find out deflection under this point load, that is point C. So we are interested to get the displacement at a point C, which is where the point load P is acting. Now we have, this is Castigliano's second theorem to find out the deflection or displacement. So delta is equal to 1 upon ei integration from 0 to L mx into dabba mx by dabba p with respect to dx. Now if we observe this particular equation, this mx stands for equation of a bending moment at a section x. Now in this case, if we see or if we observe this beam AB, here a point load P is acting at a point C. So when we are thinking about the equation of a bending moment, here when we take equation of bending moment, when we take a section between A and C, we will get different equation. At the same time, when we go to the span CB and when we take a section, here again we will get equation of a bending moment, which is a different, because there is no any constant loading from A to B. There is a change. When we are thinking about point A, here we have reaction RA. Afterwards there is no any load, but at a point C there is a point load, and afterwards again there is no any load, and then again there is a reaction B. So means we need to consider these three nodes, that is point A, point C and point B. So in this case we will classify, or we will categorize this beam into two parts, that is part AC and then part CB in this case. So for part AC, we'll try to get the equation of a bending moment separately, and for part CB we'll try to get the equation of a bending moment separately. Now to take the equation of a bending moment for a part AC, we can take a section on part AC and we'll consider its distance from A. So for this particular section, origin will be A, and then we'll try to get the equation of bending moment, which is applicable only for part AC. Similarly for part CB, again we can take a section. Now when we are taking a section, it is convenient to take the origin from point B in this case. So for part CB, origin will be B, and for part AC, the origin is A in this case. Now let us prepare one table to solve this example smoothly. Now here in this case, in this table we can see the span is there, origin is there, limits are there, then equation of bending moment is there, and then finally equation of value of dabba m by dabba p is there. Now in the span, as we discuss about, there are two spans we can consider, span AC and span CB separately. Origins, as we have discussed, for part AC the origin is A, and for part CB the origin is P in this case. Now for part AC, if we see its length, it is A now, and here we have considered origin from A, so we can say the limits for part AC, when we are going to take the integration, the limit should be 0 to A in this case for part AC, and for part CB the limit should be from 0 to B in this case. Now after this we will discuss how to get the equation of a bending moment. Now let us again consider for first part, that is part AC. When we are taking a section over this part AC, we can consider its left hand side to get the equation of a bending moment. So when we are considering its left hand side of this cross section, here we have this reaction RA. Now when we'll take its bending moment about section XX, we'll get RA multiplied by X in this case, and it creates sagging bending, so we can consider here plus sign. So here the equation of a bending moment will be equal to RA into X, and here we know that value of RA is PB upon L, so into X, and here we have used plus sign because it creates sagging bending. Now similarly for part CB, we will try to get the equation of a bending moment. Now first equation we obtained for bending moment as PB upon L into X, which is applicable only for part AC, Similarly for part CB, we can get the equation of a bending moment, as we have discussed about this section. Here we have taken a section on a length or span CB, considering the origin as a B. Now in this case it is convenient to consider the right hand side of the section instead of considering the left hand side, because we have considered origin from right end. So in this case, when you consider the right hand side of the section, again we have this reaction RB, so we can easily take down its bending moment about section XX. So here in this case, when we'll take a section here, so equation of bending moment, that is RB multiplied by X. So here you can observe for part CB, the equation of a bending moment is RB into X. We can put value of RB as PA upon L. So here we have put value of PA upon L multiplied by X in this case. Now once we get equation of a bending moment, then the rest of the example is very much simple. So in this next column or last column, here you can see we need the partial derivative of mx with respect to the applied force P. So if you observe this first equation now for part AC, here the first equation is PBX upon L. So we can take the partial derivative of this. So when we take its partial derivative, we get BX upon L in this case, and for part CB, the equation of mx is PA upon L into X, so we get its partial derivative as AX upon L. Now once we obtain value of mx and delta mx by delta P for these two span, that is part AC and part CB, then let us see how to solve the example. As we know that delta is equal to 1 upon EI, integration from 0 to L, mx into delta mx by delta P with respect to dx, which is Castigliano's second theorem. Now when we'll apply this equation for these two parts, here we know that this is the first part where integration is from 0 to A. We can put value of mx here, we can put value of delta mx by delta P with respect to dx, as EI is constant here, so you can take it outside, plus 1 upon EI. For next part, the integration limits are from 0 to B. Equation of mx or the value of mx is px upon L into ax upon L, that is the partial derivative, that is delta mx by delta P with respect to dx. Now when you will solve this particular integration, you will get the equation of a delta. So finally you can calculate, or the displacement you can calculate, delta is equal to P into a square b square upon 3 EI into L. So using this concept of strain energy, using the concept of Castigliano's second theorem, we can find out the displacement or deflection in a beam when a beam is subjected to different point loads, and we can easily find out the displacement or deflection under that particular point loads. And same concept we can use for different types of beams to get the deflection. Thank you.